Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to give an introduction to the test of homogeneity, and I will also provide a simple example to illustrate how this test can be implemented. Now, similar to the test of independence, data in this section is also presented using a contingency table. Now, in fact, the test of homogeneity follows the exact procedure as seen in the test of independence, except that when it comes to writing the null hypothesis and the alternative hypothesis. Now, when you talk about writing down the null hypothesis, the keywords that you need to have is some sort of homogeneous or the same. So the keyword here is the same or similar or homogeneous. Now the way you can write the null hypothesis is something like this. In general, it looks like this, which is the proportions of elements with certain characteristics in two or more different populations are the same. And in the alternative hypothesis, the keyword here is, of course, different, because really the hypothesis statement is just contradictory of one another. And so we can say that it is different or not homogeneous. Those are the words that you can use in the alternative hypothesis. So here we have the proportions of elements with certain characteristics in two or more different populations are different. So notice that in the test of homogeneity here, we are having more than one population. So we're talking about more than one population. It can be two, it can be more than that. All right, so that is another interesting fact about the test of homogeneity. Now, apart from that, you will see that the test of homogeneity is also a right tail test, a one-sided test, where the critical region is on the right side of the distribution, and the expected frequency for each cell has to be at least 5. This is also similar to what you have seen in the test of independence and the goodness of fit test. The statistical test is given by this formula, and also if you want to find the expected value can be found using the same formula which you have seen in the test of independence, which is big R times big C over big T. So these are all corresponds to the total values for each rows and each columns and the overall total. The degrees of freedom is also similar. You can see that the degrees of freedom can be obtained by considering R. R here is the number of rows, and C here is the number of columns. Okay, right, let's look at this example given here. We have a survey that was carried out taking one sample of 250 households from Klang Valley and another sample of 150 households in Putrajaya. So clearly, this statement here shows that we have two different populations. One is from Klang Valley and one is from Putrajaya. So the income of the households were noted and categorized as high income group, middle income group, and low income group. Using 2.5% level of significance, test the null hypothesis that the distribution of households with regard to income levels is homogeneous for the two districts. Alright, so let's start off with writing the null hypothesis and the alternative hypothesis, and you can see that here is the homogeneous. This is the keyword that actually represents the null hypothesis statement. Alright, so H null is going to be distribution of households with regard to income levels is homogeneous for the two populations or for the two districts here. And therefore the alternative hypothesis is going to be the distribution of households with regard to income levels is not homogeneous for the two districts. So that's step 1. Now step 2 is to compute the statistical test, which is given by this formula: observed minus expected, you square it, and over expected value. And we're going to start off with adding up the totals. So here we are going to have total, and this part, so we're going to have total, okay. So 70, 80, 100, the total is going to be 250. So 34, 40, 70, 76, it is going to be 150. So this is, we go back to the statement here, 250 households from Klang Valley and 150 households from Putrajaya. Now if you add up these two values here, the total of the row is going to be 104. This is going to be 120. This is 176. So if you add up this value here, it's going to be equal to 400. And similarly, if you add up these three values here, the total has to be also equal to 400. Right, in order to find the expected value, you need to follow this formula, which is R times C over T. Alright, so if you talk about this cell, now I'm just going to, okay, now if you talk about this cell, the row here is going to be, the total of the row is going to be 104, and the total of the column is 250. Multiply these two values, divide it with 400, and you will get the answer is 65. For this one, you have to multiply 120 with 250 over 400, and you will get this equal to 75. Next, for this cell, you need to multiply 176 with 250 over 400, and the answer here is going to be 110. Alright, for this cell, 104 times 150 over 400, you will get this equal to 39. And this one, 120 times 150 over 400, this is going to be equal to 45. And lastly, we have 176 times 150 over 400. This is going to be equal to 66. So these are the expected values, and we're just going to apply that right into this formula here. So the first one here, we have 70 minus 65, you square it over 65, plus next one here is this one, which is 80 minus 75, you square it over 75. Keep on doing it until the very last cell. For example, this is the last cell, so the last value is going to be 76 minus 66 squared over 66. And so the final answer is going to be 4.339. So that is the statistical test, or the test statistic. Now on the third step, we need to find the critical values. So this is considering the traditional approach. First of all, what's the degrees of freedom? Degrees of freedom is R minus 1, C minus 1. So R is the number of rows. We have 3 rows, so 3 minus 1. Next, this is 2, so 2 minus 1. And the answer is going to be equal to 2. Degrees of freedom is 2. And we know that the chi-square distribution curve, when degrees of freedom is 2, is going to look like this. more or less. And we need to find the critical value such that the area to the area in the right side of the distribution here, which is this one, this is the critical region, and the area of the critical region is 2.5%, which is 0.025. And our job is to find what is the critical value. This is the value on the horizontal axis here, such that the probability of getting this value and bigger than that is equal to 0.025. Right, so what we need to do is we need to refer to the chi-square distribution table. Alpha is 0.025 and degrees of freedom is 2. Well, you will see that for this one here, the critical value is going to be equal to 7.378. Therefore, this is the critical value, which is 7.378. Now, on the fourth step here is we need to decide whether we can reject or do not reject the null hypothesis. So that will be on the basis of comparing the statistical test with the critical value. Now you can see that this test statistic here will fall somewhere here. Okay, will be behind this value, and therefore the null hypothesis cannot be rejected. Okay, we can say that since the test statistic, which is 4.339, doesn't fall into the critical region, therefore unable to reject is null. Okay, right, next is to conclude. So we can say that not enough evidence, there is not enough evidence to say that this statement is true. Okay, so there is not enough evidence to say that. I'm not going to write down this because I'm running out of space, but what we can say is there is not enough evidence to say that the distribution of households with regard to income levels is not homogeneous for the two districts. Yeah. Okay, I think that's all for now. Thank you very much for watching.